Now I want to switch to the voltage, which is a function of the space and time coordinate, and we know that if I have the phasor representation, we have to do that we know that u of z t will be given as the imaginary value of our complex valued function u of z times the exponential function of j omega t. In our case, we will assume again that the voltage here is real, which means then we can write this is the imaginary part of u naught times the exponential function of minus j beta times z times the exponential function of j omega t. And of course these two exponential functions, the arguments will add, so we will have this is equal to u naught imaginary part of the function exponential function of j omega t minus beta times z. And if we take only the imaginary part of this function, we will get that this is u naught times sinus omega t minus beta times z. This will be, in principle, the function u of z by t. Of course, now we can have a special look, for example, at a special time instant. I will write in green color now, for example, u of z comma 0 will be equal to minus u naught sinus beta times z. Of course, what do we have now? I just want to try to sketch this here. In principle, we have here our transmission line. Of course, we know there is a coordinate system set defined along the transmission line, and here this will be the voltage in principle across the transmission line u of z comma t. And here we have the voltage distribution at a certain instant. This means I can now sketch here, for example, the z-axis. Here I sketch a u-axis, for example like this. And then, of course, this green function will show a sinusoidal distribution where the amplitude in principle is given by u naught. And it will be a sinus function we will have a sinusoidal voltage distribution, which means that, for example, at t equal to 0, the function will be 0, and then we will have here a positive value, 0 again, so this is our voltage, and of course here we will have a positive voltage here, negative here. This will be the voltage distribution for u of z comma 0. At a certain instant of time, at t equal to 0, we will have a sinusoidal voltage distribution along the transmission line. That means if you freeze the time, then, for example, at this, oh, I should perhaps sketch this zero here. It's more appropriate. Here we have a zero, and then here we have the same z coordinate. This is a zero here. That means if we have z equal to 0, then also the voltage will be 0. Here we would have a negative voltage across the transmission line. Here we would have a positive voltage, and so on. So along the transmission line, you in principle will have a sinusoidal voltage distribution. Again, or we can define, for example, this to be the total phase. Then we would have the total phase is equal to omega times omega t time minus beta times z. Of course, we could now ask what will, for example, happen with the total phase 0. So the total phase would be, point of total phase 0 would be this red point. This means we would have a 0 here, which is equal to omega t minus beta times z. And if we assume that the time changes, we can ask for the point in space where this red dot is. So we will have that beta z is equal to omega times t, or we will have that z is equal to omega divided by beta times t. So you see that this red point would then move into the positive z direction. This means it would move, for example, here, and we would have that at a certain time instant t, the whole sinus wave would move into the positive z direction. This would be u of z, t, and the velocity of movement would be given by, we define here the so-called phase velocity, phase times t, and we would have for the phase velocity, it will be equal to omega divided by beta, which is in our case omega divided by omega the square root of L prime C prime. So this will cancel, and we will have 1 over the square root of L prime C prime. So again, we can see now that this function with a negative sign here would describe a wave which travels in the positive z direction. Of course, we remember that we had a freedom to choose the sign. So if we would choose here a positive sign, then here we would have a positive sign, and here we would have a positive sign, and here we would have a positive sign. So the total phase would be here be positive. Here we would have again a positive sign. Then we would get here a negative sign, and here a negative sign. This means as soon as you consider a wave exponential function with a positive j beta z, then this describes a wave which will travel in the negative z direction. So this we will summarize again. I want to summarize the outcome up to now. So we found that for the complex valued function we have two different solutions. For example, if I have one possibility is like this, that I have a function u of z, a complex valued function, is somehow a voltage u naught times the exponential function of minus j beta, beta times z. Of course, if we change this to the real space and time function, then we will have u of z, t will be u naught times sinus omega t minus beta times z. And we saw that this is in principle a wave which travels in the positive z direction. We also have, since we have the freedom in choosing this sign, we also can have a wave like this, u of z, or a solution like this. It's u naught exponential function of plus j beta times z. Then this would result in u of z, t. It will be u naught sinus omega t plus beta times z, and we saw that this is a wave traveling in minus z direction. So we can conclude, if I have a transmission line, if I have an infinite transmission line, there are in principle always two waves possible, one wave traveling in the positive side direction and one wave traveling in the negative z direction. And of course, if I assume now just this result, so we will have that I of z is equal to 1 over zc times u of z. This means then if I would also change this into a function of space and time, I of z t will be then u naught divided by zc times sinus omega t minus beta times z. And since our characteristic impedance for a lossless transmission line is real, the current as a space and time function will be in phase with its voltage function. So today I want to discuss the difference between two approaches, especially in the case of the phase velocity. At the moment we are in principle discussing transmission line theory, and as a result we got for the phase velocity that this is proportional 1 over the square root L prime C prime. But on the other hand, we have Maxwell's theory, which will describe the electromagnetic waves in more detail, and especially there exist some solutions which are called TEM waves, and these TEM waves, especially, they correspond to the waves on our transmission line. And if you go through Maxwell's theory, then you will find for the phase velocity that this is proportional to c naught, which is the speed of light divided by the square root of epsilon r, the dielectric constant. What I assume here is, I assume here we are is equal to 1. So essentially you see in this equation for the phase velocity there is only one parameter which we can use to change the velocity, which is the dielectric constant or relative dielectric constant. But here, if you have a look to the phase velocity, you see it seems that you can choose L and C independent of each other, adjusting the phase velocity to an arbitrary value. But then the Maxwell theory is a more fundamental theory. This two phase velocity must be equal to each other. Now we will have that 1 over the square root of L prime times C prime must be equal to C naught divided by the square root of epsilon r, which means, for example, if I square the both, we will have 1 over L prime C prime will be the square root of the speed of light divided by epsilon r, which again means that we can, for example, solve for L prime. Perhaps I'll write it here. L prime will be equal to 1 over, or let's say, epsilon r divided by C naught square times C prime. This means, according to Maxwell theory, the inductive per unit length depends on the capacitance per unit length. Of course, this is from point of the transmission line from the transmission line theory. You cannot understand this result in principle, but from Maxwell theory, TEM waves means that we have transversal electromagnetic waves, which means that always the electric field and the magnetic field are perpendicular to each other. I want to explain this on a coaxial transmission line. If you have a coaxial transmission line with the inner diameter and the outer diameter, then you have, of course, here the electric field lines. Here we have the electric field. This is the E field, and the magnetic field lines form circles around the inner conductor. So these are the magnetic field lines in principle, and both fields are always perpendicular to each other. This means if you would change the geometry, though this is the magnetic field. So again, if you would change the velocity, still the electric field and the magnetic field are related to each other, because both fields must be always perpendicular in each space point, which explains, at least in principle, that you cannot choose L prime independent of C prime, but they are related by this equation. This means, normally if you go into the theory in Maxwell's equation, you can calculate the capacitance per unit length, and then with the help of the capacitance per unit length, you can calculate the inductance per unit length. This means in our further theory or transmission line theory, we will always use in principle this equation to calculate the phase velocity, which again means that we can calculate now the wavelengths on a transmission line by using this expression for the phase velocity divided by f, or this is C naught divided by the square root of epsilon r times 1 over f. So in the preceding section we will always use in principle this relation to calculate the wavelengths on a transmission line, and all other parameters, for example also the parameter beta, is related then by 2 pi over lambda. I now want to discuss the phase propagation constant, or the propagation constant of a transmission line with low losses. We will will specially discuss also the term low here. In the first step we can write the product in front of this square root, so we will have j omega L prime C prime, the square root, and then we can rewrite the square root again like this. This means we exclude j omega L, which means this is 1 minus j r prime over omega L prime times 1 minus j g prime over omega c prime. In a further step we will now assume for in RF engineering, or in RF, we see that the frequencies are quite high, so that we will assume that low losses means that the term R prime over omega L prime is small compared to 1, and also the term G prime over omega C prime is small compared to 1, which means we will get here, this is 1 over j, the square root of L prime C prime, times the square root of, here we have first 1 times 1 gives 1, and then we have minus j r prime over omega L prime time minus j g prime over omega c prime, and there would exist a second term r prime times this term, which is according to this approximation a term of higher order, of second order, which we will neglect, so that we do say this will be our approximation we use. And now we will do a further approximation from mathematics. We know if I have something like this, 1 plus epsilon, where epsilon means this is a small number, we can always write like this is 1, or do an approximation 1 plus 1 half epsilon. And this approximation we will use here, so we can say this is round about j omega L prime times C prime, and here we will do the approximation for the square root like this. This is 1 minus j r prime over 2 now omega L prime minus j g prime over 2 omega c prime. Or in the next step we can conclude, do it like this, that we have gamma. It's equal, of course, here you see j omega, the square root of L prime C prime. This is this times 1. And of course then we will have plus, because j times j becomes minus, and minus is plus, and then we will have here r prime over 2 omega L prime times omega L prime C prime plus corresponding here G prime divided by 2 omega C prime times again omega times the square root L prime C prime. And in this expression, of course, this will cancel against this will cancel against this, and of course we can also cancel L prime here. And you see here we have two parts, we have one imaginary part and one real part, which we can say the imaginary part, this will be beta, which we already know, is J omega L prime C prime according our transmission line system. And in the chapter before, oh sorry, here it's not J but omega, and before we use that this is 2 pi over the wavelengths, so we, according to Maxwell's theory, we have to calculate the wavelength, and this will result in a certain beta. And the second term will be that we have alpha, it will be r prime over 2, and here you will see this is the square root of L prime divided by C prime, which is again our characteristic impedance of the lossless transmission line, plus G prime over 2 times again set C of our lossless transmission line. We see here that perhaps that we have two terms now, beta will be given always by this equation, also for a lossless for a transmission line with low losses. This means the phase propagation is equal to the lossless transmission line, but what we will get is we will get a damping coefficient. This means this we will discuss later, and we will get for gamma in total now. Gamma, the wave propagation constant will be alpha plus J beta. And this we will again have a look what will do. Alpha will in principle damp our wave. Now I want to discuss the influence of our alpha, of the value of alpha on our function of space and time. According to this equation, we know we can switch from our complex valued function to the function of space and time, and we will see the following, that of course the voltage will be the same. Of course this will describe in principle the voltage of our transmission line wave, but according to this function the voltage of the transmission wave will decay in the x direction. So I will draw this. Now this term will reside in a decay of the amplitude. This means we have an exponential decay of an amplitude which looks almost like this. While the second term still is the same as in the case of a lossless function, lossless transmission line, which means this term describes the wave propagation. So for example, for the certain time instant u of z t equal to 0, we will get the already known sinusoidal distribution, which will almost look like this. This means alpha will result in a decay of the amplitude as the wave propagates along the transmission line. For example, if we have here u of z, t, and we assume that the wave propagated a little along the z direction, we will almost have this voltage distribution. So we have here. This means the amplitude of our wave will decay as the wave propagates along our z direction. Here, though this is the interval, or the space will be equal to the phase velocity times t. So as soon as the wave now travels along a transmission line with low losses, part of the energy of the wave will be transferred into heat in our transmission line. In the last step, I want to discuss the characteristic impedance of a transmission line with low losses. In the first step, we saw that the transmission line, the characteristic impedance of a transmission line is a complex value depending on R prime and C prime. But at this point we didn't use our approximation, so in the next step we will reuse this approximation. This means we will have here 1 over omega L prime divided by 1 over omega C prime times the square root of, here you have again 1 minus j r prime over j omega, sorry, not j here, but omega L prime divided by 1 minus j g prime divided by omega c prime. And here we can again use our approximation. This means here in this term j omega and j omega will cancel, and we will get in principle the square root of L prime C prime, which means this is equal to our characteristic impedance of the lossless transmission line times 1 minus j, and here you have R prime divided by 2 omega L prime divided by 1 minus j g prime divided by 2 omega c prime. So you see here again, with increasing frequencies both terms will vanish, and also they cancel by its phase. So in principle you must figure out by experiment at what frequency, or what will be the limit for the frequencies where the characteristic impedance becomes a real value, and one finds, so I will write here, proof by experiment for, and the frequency, as soon as you have encounter frequency greater than round about 10 kilohertz, we will find that our characteristic impedance is given by C. It's equal to the L prime over C prime, which is a real value. This again means that above 10 kilohertz always the voltage wave will be in phase to the current wave, and vice versa. Though if we assume now for a transmission line with low losses, we found that the wave voltage as a function of the z coordinate will be given by somehow a constant times the exponential function of minus gamma times z, where gamma is composed by alpha plus j beta, and we will have that the current function itself, it will be 1 over the characteristic impedance, which again is a real value, and which means this function will be in phase with this function, and we will have here u of z. This, of course, this will describe a wave which travels in the positive z direction, and we already know that if we use a different sign here, the positive sign, then we can describe a wave in the negative z direction. So this is in principle now the solution for a transmission, or for waves on the transmission line with low losses.